Homework 16 asks, starts by asking you how to prepare a pure dry sample of copper nitrate from copper carbonate. Now, these salt production, preparing a sample of a salt seems to come up quite a lot. So I thought it was a good time to remind you of this page from earlier in the book, because it's quite a nice summary. I love these summary pages because they get a lot of lessons work onto one page, and they're a bit easier to revise and learn. So summary of preparation of pure dry salt. So we've got three different reactions we need to know about, three different methods we need to know about. So the first one is insoluble, where we start with an insoluble reactant and a soluble reactant. It's a bit of a mouthful, isn't it? An insoluble reactant and a soluble reactant. And they make soluble products. So the products are soluble products. Hopefully you can see that. I've written that a bit small. Right, an example. Let's give you an example. It's probably easier to see an example. This was the core practical, the one you need to know most about. So copper oxide. Copper oxide is the insoluble, and sulfuric acid. So they are the reactants. Let's give you a symbol equation. So CuO, that's the solid, plus sulfuric acid, H2SO4, that's aqueous, that's soluble, makes copper sulfate, aqueous, plus water, H2O, liquid. Okay, so that's the example. So how do we get a pure dry sample of copper sulfate? That's what we're trying to do. Prepare a pure dry sample of salts. So we want to prepare copper sulfate. Right, so there's 4 stages to this. First stage, mix. You're going to mix the and we're going to use an excess, too much copper oxide. So we're going to mix the reactants, copper oxide and the sulfuric acid. So if you want to draw a diagram of that, feel free. Have a beaker there, and we're just going to simply have a stirring rodding. So we're going to stir it as well to ensure it reacts. And we've got our excess copper oxide, and we've got our sulfuric acid in there as well, H2SO4. Once we've mixed it, we want to make sure all the sulfuric acid reacts, so we're going to warm it up. Okay, so to warm it up, we'd put that on a tripod and we would heat it. So that's our warming. After we've done that, we want pure copper sulfate. So to have pure copper sulfate, we've got to get rid of the excess, the too much copper oxide. We do that by filtering. So we can have a filter funnel, filter paper. So our copper oxide, our excess copper oxide is going to be there. And down here is going to be the solution of copper sulfate, because we've made copper sulfate in water now, CuSO4 aqueous. And finally, to get the copper sulfate away from the water, we need to evaporate. And we can have a diagram of that. Again, we have a tripod, and we're going to heat under the tripod. On top of the tripod, we're going to have an evaporating basin. And that will drive off the water, and we're just going to be left with our copper sulfate crystals. And there's our pure dry sample. Next type of reaction is where all the reactants and products are soluble. Okay, this is a much more difficult method. An example would be sodium hydroxide. Sodium hydroxide is soluble. It's an alkali. It's going to react with hydrochloric acid, which is, again, soluble. It's aqueous. And that's going to make sodium chloride, which is soluble, and water, which is a liquid. I'm just going to put H2O down. And water, which is a liquid. Let's give a symbol equation for that. NaOH, aqueous, plus HCl, aqueous, makes sodium chloride, NaCl, aqueous, and water, H2O, liquid. Okay, much more difficult. For this one, we need to titrate. Okay, the most important thing is we titrate, and for a titration, we need a burette. Long, thin tube. Okay, tap at the bottom, fill that with acid, and we're going to titrate that against the alkali in the beaker down here. So in here, we're going to have alkali, and it's going to be a measured amount of alkali. I would measure it out using a pipette. Again, a very long, thin tube, a little bit of a bulb in the middle. Okay, and that measured out exactly 25 centimetre cubed alkali. So that's called a pipette. This is called a burette. Okay, and we're going to add some phenolphthalein to that as well. Phenolphthalein. Phenolphthalein is an indicator. Now, when we add an acid to an alkali, we neutralise. So the phenolphthalein will tell us when all the alkali has been used up. At that point, we stop adding the acid. And at that point, we have exact amounts of acid and alkali. So the important point with this one is exact amounts of acid and alkali, and both reactants. We need exactly the same amount of both reactants. Okay, so we do that by titration with phenolphthalein. Titration using phenolphthalein indicator. You can use other indicators. Avoid universal because the colour changes aren't obvious. Titration using phenolphthalein indicator. Once we know that neutralisation point, once we know neutralisation, then repeat without the indicator, okay? And that's important because we want a pure sample of that salt, the sodium chloride. If we stop once we've got phenolphthalein indicator in there, we've got salt and indicator. So once we know that neutralisation point, we're going to do the whole thing again. But we're going to do it without indicator. Now, we won't see the neutralisation point because there's no indicator, but we know it's the neutralisation point because we did it previously. After you've done that, you've got sodium chloride and water, so we want to evaporate. And that's the second one. Last one is where we have soluble reactants, and insoluble, and well, I should say one insoluble product. Okay, an example there would be silver nitrate, and and that reacts with something like sodium chloride. Let's put the word down. Sodium chloride. Now that makes sodium nitrate, which is soluble, and silver chloride, which is not. That's a solid. So it precipitates out. So I'll give you a simple equation, AgNO3 plus NaCl, all soluble. So that's soluble, aqueous. That's soluble, aqueous. That's going to make sodium nitrate, NaNO3. That's soluble, aqueous, plus AgCl, and that is a solid. So we want a pure dry sample of that solid there. Okay, so the way we do that, first off, we mix. Doesn't have to be exact quantities. Just going to mix the silver nitrate and the sodium chloride. Okay, when that happens, we're going to get a soluble product and a solid. So we want to get that solid out, so that's easy. We filter, and that gets that silver chloride out. And you can draw a little diagram now. I'm quite a fan of drawing little diagrams next to these things, no matter how messy they are, because just the act of drawing a diagram helps you remember it. So you're going to have that solid there. That's going to be the solid, and all the product, the silver nitrate solution. Okay, the solutions are going to be down here, and of course there'll be one of these will be in excess, and whichever that is, that will be down here as well. But this will be wet and dirty with, what's the word I'm after? Polluted, I suppose, or contaminated, possibly contaminated is best, contaminated with sodium nitrate, sodium chloride, silver nitrate, maybe, any of these soluble reactants. So the next thing we have to do is wash it. Okay, so the way we're going to wash that is we just get some distilled water, or deionized water. Distilled water is good because there's no salts in distilled water. So you have a squeezy bottle, and that's just full of water. Okay, you wash it with distilled water. And that just cleans any of those unreacted reactants off, and mainly the sodium nitrate off it. So wash it, and then after you've done that, you're going to dry it. Open the filter paper up and dry it. So mix, filter, wash, dry. That's the important things there. That's square off the important things. That's important. So they're the important things, and you can pick the important ones out of that middle one. Now, the answer to this homework question is on here. Okay, so have a little reminder of that. Next one. So, bit of electrolysis now. Hydrochloric acid can be electrolyzed using this apparatus. Okay, hydrochloric acid is the solution in there. Okay, and it's going to make gases. There's our positive electrode, there's our negative electrode, and those gases are going to bubble up here and be collected in these test tubes. What happened during electrolysis? The reactant, and this happens during every electrolysis, the reactant decomposes, breaks down, and produces elements. Okay, so the reactant is broken apart into its constituent elements. Is the power supply direct current or alternating current? Well, it has to be direct current. We have to have a direct current. What are the names of the positive and negative electrodes? Well, one's the anode, one's the cathode. You're going to have to figure that one out. What gases are formed at the positive and negative electrodes? Well, with this reaction, we've got, I'll tell you that's going, hydrogen and chloride in hydrochloric acid is going to be hydrogen ions and chloride ions. The hydrogen ions are positive, the chloride ions are negative. Now, one of those is going to make hydrogen, and the other one's going to make chlorine, and its opposites attract. So hopefully that helps you there. What mass of hydrogen gas is produced when 5 moles of hydrochloric acid are electrolyzed? Okay, so another moles calculation. Okay, it's 3 stages to moles calculations, as you always know: moles, stoichiometry, and moles. Okay, moles comes first, and you're now thinking to yourself, moles equals mass over MR, and you're starting to say to yourself, hang on a second, there's no moles here. What mass of hydrogen gas, let's put the question mark on the hydrogen gas, that's the first thing we do, is produced when 5 moles, we've got 5 moles of hydrochloric acid, 5 moles, not a mass. They've actually done this first stage for you here, the answer's 5. Nothing to do at all, it's been done for you. Stoichiometry, straight on stoichiometry, 2 HCl makes 1 H2. Well, 2 makes 1. How do we get from 2 to 1? We divide by 2. So you don't start with 2, you start with 5 from this stage here. Bring the 5 down. 5 divided by 2 makes how many moles of hydrogen? You work that out. Last stage, moles. We need to rearrange the equation. Mass equals moles times MR. Well, there is whatever answer you came up with in stage 2, that's going to go there. You need to multiply it by the MR of hydrogen. Well, the atomic mass of hydrogen is 1, and you've got an H2 molecule by the MR of H2. See if you can get an answer there. Next, water can be electrolyzed using this apparatus. Okay, so we've got water in here now. Well, there's water. Water breaks into hydrogen and hydroxide ions. Okay, there's our positive electrode, there's our negative electrode. Okay, what gas is produced at both? Well, water's going to break down into hydrogen and oxygen. The hydrogen ions are going to be at the positive or the negative electrode, or opposites attract. You figure it out. Test, well, I'll tell you the 2 tests. You need to work out which is which. One's a lit splint and squeaky pop, and there's 2 marks, one for lit splint, one for squeaky pop. And the other is glowing splint and relights. Well, you need to decide which is which. Compare and use the reaction equations to explain the relative proportions of gases produced in the 2 experiments. Okay, let's just quickly go look at this one here. This is H2O. Okay, it's going to break down into H2 and O2. Okay, balancing this equation, 2 water molecules are going to make 2 hydrogen molecules and 1 oxygen. So in this equation here, we've got 2 moles of hydrogen and 1 mole of oxygen. Well, you've got twice as much of one gas as the other. That's the relative proportions, twice as much to one, and we can see that in the equation. If you go to the other equation, we've got hydrochloric acid electrolyzing, and it breaks down. That's going to break down to hydrogen and chlorine. Balancing that equation, 2 moles of hydrochloric acid make 1 mole of hydrogen and 1 mole of chlorine. We've got exactly equal numbers here and here, 1 and 1, and the quantity in both of these is the same. Okay, so hopefully you can see the relative proportions are the same in the equation and the same in the product, in the reaction, whereas here it's twice as much one as the other. Anyway, try and explain that. Good luck.